Welcome to my video lecture. This is Amarnath, Assistant Professor in Mathematics, Department of Humanities and Sciences. Under the course Linear Algebra and Calculus, we are discussing the second part of the diagonalization of a matrix. In the last previous class, we have studied about the diagonalization of a matrix we have done. How to diagonalize a given square matrix. It is a transformation of given matrix to particular diagonal form. Right? For any matrix A is given, that is a, let us say 3 cross 3 matrix, it have some elements, then we are transforming to particular diagonal form. But only diagonal element will be there, remaining elements 0. That we are calling diagonal matrix, right? So this we have done in the last class. And apart from that one, we have done application of the diagonalization, how to find higher powers of a matrix. That also we have done in the previous class. So continuation to that one, in the present lecture, we are going to learn algebraic multiplicity and geometric multiplicity of an eigenvalue. So it is an important topic, and with that one we have an application. We can say whether the given matrix can be diagonalized or cannot be diagonalized. That depends on algebraic and geometric multiplicity. So today we discuss about these two things. Now let us define the algebraic multiplicity and geometric multiplicity of an eigenvalue. Now, for the given matrix, generally we used to find eigenvalues, eigenvectors. Based on the eigenvalues and eigenvector, we can decide what is the algebraic multiplicity, what is the geometric multiplicity. First, let us discuss the algebraic multiplicity. Right? This is suppose if lambda is an eigenvalue of order t, and is this one order t, let us say second order, third order, like that, then of the characteristic equation of matrix A, then the order t is called algebraic multiplicity of an eigenvalue lambda. For any particular eigenvalue lambda, how many times we are getting the particular eigenvalue, that we can say order. So the number of times an eigenvalue, briefly to make you understand easy language, the number of times an eigenvalue is repeated for the particular matrix A, that can be treated as the algebraic multiplicity. Let us say we have taken one matrix A, which is a 3 by 3 matrix. For this 3 by 3 matrix, I got eigenvalue lambda is equal to 1, 2, 3. See here, these 3 means the characteristic equation particular to this one, lambda 1 minus 1, lambda minus 2, lambda minus 3. We have the experience how to find the eigenvalues and eigenvectors. There we get this type of characteristic equation. From there we find eigenvalue lambda. This lambda is 1, 2, 3. At a 3 eigenvalues we got. The lambda 1 is power 1, only one time. 2 at a 1 time power, lambda minus 2 power 1, lambda minus 3 power 1. That is the order. Order of the 1 is 1. Order of the 2 is 2, 1. Order of 3 is 1. In particular, for each eigenvalue, here the algebraic multiplicity for lambda is equal to 1, that it is repeated only one time, or the power of lambda minus 1 is 1, the order 1. So algebraic multiplicity of lambda is equal to 1 is 1 only, because repeated only one time. So lambda is equal to 2, also 1. Lambda is equal to 3 is also 1. What is the algebraic multiplicity of these particular 3 eigenvalues? For 1, 1, for 2, 1, for 3, 1. Let us take another example. So this particular example, suppose you got eigenvalues for a particular given matrix, we got 2 comma 2 comma 4 we got, right? Here nothing but lambda minus 2 whole square, characteristic equation. How could be the characteristic equation? Means lambda minus 2 whole square, lambda minus 4. Then only we get 2 eigenvalue 2 times. Now here order of the 2 is 2, order of the 4 is 1. Then the algebraic multiplicity of for lambda is equal to 2. What could be the algebraic multiplicity? That is how many times it is repeated, or order of the lambda minus 2 factor is 2. That's why here algebraic multiplicity of 2 is 2. Nothing but 2 times repeated. Next, lambda is equal to 4. How many times we have 4 in the equation? Only one time. That is the algebraic multiplicity of 4 is 1. Very simple. When you find eigenvalues, automatically you can say algebraic multiplicity, the order of the eigenvalue. So 1 time repeated, or 2 times repeated, or 3 times repeated. That could be the algebraic multiplicity of the particular eigenvalue. Let us define the geometric multiplicity. So geometric multiplicity of a particular eigenvalue, right? Here clearly the definition is very simple. The number of linearly independent eigenvectors corresponding to the particular eigenvalue is called a geometric multiplicity of that particular eigenvalue. How many independent eigenvectors you are going to generate or you are going to get to the particular eigenvalue is called as the geometric multiplicity. Algebraic multiplicity is related to eigenvalue. Geometric multiplicity is related to eigenvectors. How many linearly independent eigenvectors you are getting to particular eigenvalue, that we are calling it. That should be linearly independent. Dependent vectors will not be considered. One vector should not depend on another vector. Such type of independent vectors we count. How many you are generating, that will be the number of eigenvectors will be called as a geometric multiplicity. So example, let us say for lambda is equal to suppose 3 comma 3 comma 5. So here, and one other example, lambda is equal to 2 comma 4 comma 6. See here, in this example 2, here all are independent eigenvalues. So that means here 2, 4, 6 are distinct eigenvalues. Then algebraic multiplicity, geometric multiplicity both will be equal. For a distinct eigenvalue, that is here lambda is equal to 2. Definitely how many eigenvectors you are going to get? Only one eigenvector. It is a distinct one. Already we have discussed that one. So lambda is equal to 4. It is a distinct one. How many eigenvectors you are going to get? Only one eigenvector. For lambda is equal to 6, only one eigenvector. So then in particular here, any particular eigenvalue, we are going to get only one eigenvector. Distinct eigenvalues, always eigenvector generated are linearly independent. So if one time repeated eigenvalue, there is no doubt, only one eigenvector we are going to get. Means in this case particularly, for each eigenvalue, algebraic multiplicity is equal to 1, geometric multiplicity is equal to 1, not repeated case. Okay. In this one, algebraic multiplicity is equal to and geometric multiplicity is equal to 1, both are equal. Whereas in lambda is equal to 3 comma 3, 2 times we got, then algebraic multiplicity of lambda is equal to 3, it is 2. But whereas geometric multiplicity can be 2 or maybe 1. It can be, we may get 2 eigenvectors, we may get 1 eigenvector, depends on the matrix and the problem. There is no rule, it is 3 repeated 2 times, we have to get 2 eigenvectors. We may get 2 or we may get 1. The meaning is number of linearly independent eigenvectors, that is will be maybe equal, maybe less than. That we are calling as a geometric multiplicity is less than or equal to algebraic multiplicity, right? That we are going to discuss. So clearly for any particular eigenvalue, this property holds. Geometric multiplicity is less than or equal to algebraic multiplicity. In which case, whereas distinct, second example, distinct eigenvalues are there, it will be equal. No doubt in that one, no need to verify. Distinct eigenvalues are there, algebraic multiplicity is 1, geometric multiplicity is 1. Only in the case of repeated eigenvalues can be equal, maybe less than. So that we are calling as geometric multiplicity is less than or equal to algebraic multiplicity. Now our coming topic, can be diagonalized or cannot be diagonalized, that depends on this relation. So distinct eigenvalues are there, then you are getting equal number of eigenvalues, equal number of eigenvectors. Then that matrix can be diagonalized. And the geometric multiplicity is equal to algebraic multiplicity, then the matrix can be diagonalized. Suppose it is less than that, right? Look at this one. Here in this case, a less than or equal to will be there. Equal to case we can diagonalize. But geometric multiplicity is less than algebraic multiplicity. That matrix cannot be diagonalized because you are getting the sort of eigen vectors. We can't diagonalize the matrix. So here in the next slide, I am going to show very clearly. See. So in the previous class, we discussed about the diagonalization of a matrix. What is that one? A matrix is diagonalizable if there exists an invertible matrix P such that P inverse AP is equal to D. What is the P? P is the model matrix which transform the A matrix to D, which is a model matrix which contains the eigenvectors x1, x2, x3. Suppose it is a 3 by 3 matrix, 3 eigenvectors you are getting, you are going to form model matrix and it can be diagonalized. Suppose for any given matrix repeated roots are existing, we got only x1, x2 and x3 we are not getting, right? Then you can't diagonalize. At algebraic multiplicity, geometry both are equal, that is the first case, equal number of eigenvalues, equal number of eigenvectors, you can do diagonalization. But geometric multiplicity is less than algebraic multiplicity, then it cannot be diagonalized, okay, cannot be diagonalized, less than, equal to can be diagonalized, geometric multiplicity equal to algebraic multiplicity, it can be diagonalized, less than, vectors are short, so we cannot diagonalize. Why? Because the model matrix for the diagonalization which we are using, that we required equal number of eigenvectors which form the model matrix. So the main concept of this topic, the student has to remember, this geometric multiplicity is less than algebraic multiplicity, it cannot be diagonalized. That we discuss very clearly with an example, right? Let us go to the one small example. So look at this one, he is asking, show that the matrix, particular given matrix, it is a what order matrix, 3 by 3 matrix, cannot be diagonalized. So can be diagonalized, we have done many problems. So cannot be diagonalized, let us check it. So the solution, let us see. So this can happen, can be diagonalized or cannot be diagonalized, that depends on the eigenvalues and eigenvectors. Let us find eigenvalues and eigenvectors, then we can decide. The characteristic equation of A is det of A minus lambda is equal to 0, okay, right? That how to do this one we know very well. Many previous classes we have done eigenvalues and eigenvectors. So that is det of this lambda should be subtracted from diagonal elements, remaining elements no change, 2 minus lambda, 3, 4, 0, 2 minus lambda, minus 1, 0, 0, 1, which is equal to 0, right? It is a diagonal matrix. So determinant can be determined very easily. How to find? That is product of the principal diagonal elements. Since it is a diagonal upper triangular matrix, the determinant for upper triangular matrix, for lower triangular matrix, for diagonal matrix, the determinant is equal to product of principal diagonal elements. What are the principal diagonal elements here? 2 minus lambda, 2 minus lambda, and here it is a 1 minus lambda. Minus lambda is equal to 0, right? So since 3 factors are there, we will be getting 3 roots, that are lambda is equal to 2, 1 are the eigenvalues. Now these 3 eigenvalues are not distinct. If it is distinct, we no need to discuss anything, simply we can say it can be diagonalized. Distinct eigenvalues, distinct eigenvectors can be generated. But here 2 eigenvalues are repeated. So one eigenvalue, particular eigenvalue 2 is repeated 2 times. Then we have to check how many eigenvectors we are going to get for lambda is equal to. For lambda is equal to 1, there is no doubt, definitely we get 1 eigenvector. Then lambda is equal to, we are getting 2 eigenvectors, 1 eigenvector. Suppose we are getting 2 eigenvectors, algebraic multiplicity 2, geometric multiplicity 2, it can be diagonalized. Otherwise, it cannot be diagonalized. Like let us check it now. For lambda is equal to 2, corresponding eigenvector. How will you find? A minus lambda I into x is equal to 0. That is a formula to find eigenvectors. Then subtract, put lambda is equal to 2, then subtract in the diagonal elements, then it is 2 minus 2, 0, 3, 4, 0, 2 minus lambda, 2 minus 2, 0, minus 1, 0, 0, 1 minus 2, minus 1. So x and particular eigenvector we are finding, that we are calling as x1, x2, x3. 0 means null matrix, which is column matrix. 0, 0, 0. We need to solve it. So, whenever we need to solve, this should be transformed to echelon form, because to solve the homogeneous system, we need to reduce the coefficient matrix to echelon form. Here see, in the second row 2 zeros, third row 2 zeros, it is not in echelon form. Then this element, third row, third element should be done 0. That is very simple. R3 implies R3 minus R2. Using R2 I am doing. Then here 0, 3, 4, 0, 0, minus 1. R1, R2 no change. R3 minus R2. 0 minus 0, 0, 0 minus 0, minus 1, minus of minus 1, plus 1, 0, which is equal to x1, x2, x3, which is equal to 0, 0, 0. Right? Now look at it, it is in echelon form. It is in echelon form means what is the rank of the matrix here? Very clear. Rank of the matrix here, rank. So 2 non-zero rows. One row is a 0 row, last row. So rank of this coefficient matrix is 2. Then here number of unknowns, how many? 3. Then homogeneous system, we have the rule, if R is less than n, if R is less than n, how many arbitrary constants we are going to get? That we have a formula n minus r. N minus r means the number of unknowns are 3, rank is 2, the difference is 1. The difference is 1, so we have to select one arbitrary constant. Select one variable as arbitrary constant. Only one variable as arbitrary constant. As arbitrary constant. Right? Arbitrary constant. At the same, let us say x3, since we are unable to find x1, x2, x3, see this x3 we can find, right? X2 we can find, maybe we may be missing x1 or any other one we can take. Let us take x1 is equal to k. X1 is equal to k be the arbitrary constant, or we can take x2 is equal to k, x3 is equal to k. Means how many eigenvectors we are going to get? Only one eigenvector in terms of k. Say if the let us multiply 0 into x1, 0, 3 into x2, 3x2 plus 4 into x3, 4x3 is equal to 0. Next, minus 1 into x2, minus x2 is equal to 0. It implies x2 is equal to 0. X2 is equal to 0, x1 is equal to k. Put x2 is equal to 0 here. So 0 plus 4x3 is equal to 0. And x3 also 0. Right? Now what is the eigenvector? X is equal to, how many eigenvectors we are getting? x1, x2, x3. x1 means k, which we have taken as arbitrary constant. Then since x2 0, x3 also 0. Then we got one eigenvector, k 0, 0, one eigenvector. But lambda is equal to, here it is repeated 2 times, 2 comma 2. Right? Here for lambda is equal to particular. But here we are getting only one eigenvector we are getting. Geometric multiplicity is 1, algebraic multiplicity is 2. So clearly for lambda is equal to 2, what is the algebraic multiplicity is 2, because it is repeated 2 times, lambda minus 2 whole power 2. Then how many eigenvectors we got? Linearly independent eigenvectors, how many we got? 1. Geometric multiplicity is less than algebraic multiplicity, right? For lambda, so we can, what about the lambda is equal to 1? That is a distinct eigenvector, eigenvalue. Definitely you will get one more eigenvector. So that is total here for this lambda is equal to 1, algebraic multiplicity is 1, and geometric multiplicity, here no need to find eigenvector, directly we can say it cannot be diagonalized because only one eigenvector. But how many eigenvectors total we are getting? For lambda is equal to 1 eigenvector we are getting, for lambda is equal to, we are going to get one more eigenvector, totally 2 eigenvectors. So the model matrix required for diagonalization is x1, x1, x2, x3. But this x3 is short, we are getting only x1 and x2. Clearly for one particular eigenvalue, geometric multiplicity is less than algebraic multiplicity. we have discussed, that is, we have the rule, geometry is less than algebraic multiplicity, it cannot be diagonalized, right? So for the given problem, therefore, given problem cannot be diagonalized. Given product, given matrix cannot be diagonalized. Cannot be diagonalized. Okay. Right. So let us one more problem you can practice on this one. Let us take one more example here. I am giving second one. Find the algebraic and sometimes the used to ask algebraic and geometric multiplicity of the particular matrix. In that case, you need to find again eigenvalues and eigenvectors. So this problem I am giving for the practice purpose. Look at it, is a 3 by 3 matrix, right? This 3 by 3 matrix, what are the eigenvalues, what are the eigenvectors, that I am giving directly here. Lambda is equal to here we are going to get eigenvalues -3, -3, 5 are the eigenvalues, right? And eigenvectors we need to find. For lambda is equal to 5, we are going to get one eigenvector, no doubt. For lambda is equal to -3 comma -3, how many eigenvectors you are going to get? Suppose you are getting 2 eigenvectors, then it can be diagonalized. Suppose you are getting only one eigenvector, it is repeated 2 times, only one eigenvectors, it cannot be diagonalized. So that you can verify with the eigenvector. So for 5, you don't need to discuss, it is a distinct eigenvalue, one eigenvector definitely we get. For lambda is equal to -3, how many we are going to get? So then what is the formula for to get eigenvectors? A minus lambda I into x is equal to 0, that is the formula, right? So put lambda is equal to -3, that is from the diagonal you need to subtract the -3 to get that matrix, right? Look at this one, -2, -3, 2, -3, 2, 1 -3, -6, -1, -2, 0 -3 into x1, x2, x3, which is equal to 0, 0, 0, right? Then simplifying, -2, -3, -5, 2, -3, 2, 1 -3, -2, -6, -1, -2, -3, x1, x2, x3. Next RHS column matrix 0, 0, 0, right? Here I am going to simplify. Then since it is a, I said in the clearly previous lectures how to find the eigenvectors. There we can do in 2 ways. One is shortcut method, that is a cross method we can do. Otherwise, like original method for homogeneous system, change the matrix to echelon form, right? If you change to a echelon form, what could be the answer here? Let us calculate now. So here using the first row element -5, we need to make below 2 elements 0. That is the echelon form method we know very well. R1, using R1 we have to make R2. R2 implies R2 is a 2 multiplied by 5, 5R2. So plus 2R1. 5R2 means 5 to the 10. 2R1 means -10. -10 plus 10, 0. Next R3 implies, so that is 5R3 minus R1. 5R3 means 5 into -1, -5, minus or minus, plus 5, -5 plus 5, 0. That is, let us write this one. First row we are not any change, -5, 2, -3. Second row we are doing change. 5R2, 5 into 2, 10. Next 2 into -5, 10. 10 minus 10, 0. 5R2, 5 into -2, 5 into -2, -10. Next 2R1, 2 to the 4, -10 plus 4, that is a -6. Next 5R2, 5 into -6, -30, plus 2R1, 2 into -3, -6, -36, right? Last row, 5R3, 5R3 minus R1, 5 into -5, minus 5. Next plus minus R1 plus 5, that is 0. Next 5R3 again, 5 into minus 2 minus 10, 5 into R2 minus 10, 5 minus R1 minus 2 minus 12. Next 5R3, 5 into minus 3 minus 15. Here we can calculate 5 into minus 3 minus 15 minus R1 minus of minus plus 3, that is minus 15 plus 3, that is minus 12. Okay, so we can calculate very simply. Again, is it in echelon form or not? Check it. So is a 1 0 1 0, it is not in echelon form. The number of zeros before the non-zero entry should increase. So here 1 0 1 0, it cannot be. So x1 x2 x3 0 0, right. Right, let us take again using this R2 element, I will make this R3 element 0. That is echelon form procedure, you know very well. R3 implies R3 is minus 12 plus 2R2, 5 into R3 is minus 12 and this is both are same sign, subtract. So that is minus. Now how much you are going to get? First row we are not changing, minus 5, 2, minus 3. Next 0, R3 minus 6 minus 36, R3, R2 we are not changing, R3 we are changing, R3 minus 2 R2, 0 minus 0 0, minus 12, minus of 2 R2, minus of minus plus 12, that is 0, R3 minus 12, minus 2 R2, minus of minus plus 2 R2, 2 into 36, 72, 72 plus 72 minus 12, 60. So x1, x2, x3 is equal to 0. See, so clearly here it is in echelon form, 1 zeros, 2 zeros, it is in echelon form. Then we can decide the rank. What is the rank? Number of non-zero rows in the echelon form. That is here 3 non-zero rows are there. The rank is 3. Number of unknowns. How many unknowns? And rank is 3. Unknowns also 3. N minus r is equal to 0. Right here. Then definitely here we are going to get the 2 eigenvectors. That we can find the 2 eigenvectors and we can do. Right. So number of eigenvalues, number of eigenvectors, geometric multiplicity and algebraic multiplicity both are equal. We can say that is it can be diagonalized. For a 5 you cannot, you need to find. So this is here algebraic multiplicity and geometric multiplicity. In this way we can find the geometric and algebraic multiplicity for the given problem. So in this session we have discussed about the particular given matrix algebraic multiplicity and geometric multiplicity. And it is nothing but to find eigenvalues and eigenvectors. Just if you determine based on the eigenvalues, we can tell algebraic multiplicity. How many times it is repeated, 1 time or 2 times or 3 times. Geometric multiplicity, for particular eigenvalue, how many linearly independent eigenvectors we are getting. That is the geometric multiplicity. Suppose both are equal for any particular eigenvalue, it can be diagonalized. So less geometric multiplicity is less than the algebraic multiplicity, it cannot be diagonalized. So then we can discuss about the diagonalization for real symmetric matrices in the coming class. It is a little bit different procedure when you compare to the ordinary matrices. A real symmetric, A transpose is equal to A symmetric matrix and no complex elements are there. For this matrices, how to do the diagonalization, that will be discussed in the diagonalization part 3. Okay, thank you.